Hello, in this video I would like to show you how to create a model of a plug-flow reactor, or you can say mixed flow reactor if we add diffusion to it. So the system that I'm going to try to create is going to be quite simple. So we're going to have a kind of a plug-flow reactor. The geometry and other properties are given here in this on this figure. So there's a constant flow going through the system. I'm going to assume that the cross-sectional area of the plug flow reactor is 1 square meters, and the flow is a constant flow of 100 cubic meters per day goes through it. The length of the plug flow reactor is 200 meters, and then I'm gonna run it for two kind of scenarios. In the first one, it's going to be a conservative tracer, and the second one, it's going to be a basically a basic chemical undergoing first order reaction or first order decay with a rate constant of 0.1 per day. So I actually need one more piece of information here. So let's assume that let's do it here. I'm going to assume that the concentration of, let's say, any chemical, I'm going to here consider BOD, biochemical oxygen demand, but it can be anything. So I'm going to say the BOD concentration is, I don't know, let's say 4 milligrams per liter, something like that. So that's what essentially the boundary condition will be. So I think all the information is given here, and what I'm going to do is that in GIFMod, of course, we don't have a one-dimensional component, so we have to essentially represent this as a number of segments basically connected to each other. So what I'm going to do is that I will represent this using 10 blocks, each of them having a length of 20 meters. Now that will produce some level of numerical diffusion. So I just want you to be aware of that. And there's no way that we can completely eliminate numerical diffusion. But of course, if you use smaller segments or smaller elements, we're going to have smaller numerical dispersion. However, that will increase the computational burden, or it's going to take a little longer for the simulation to be run. Anyways, so let's get started. Now let me start GIFMod. So here's my GIFMod window. Now to start, basically I can use several of these blocks to do my thing. I can use pond, or I can use stream segment. Now in this case, I'm going to use a stream. So I'm going to first create my one block, okay, with a length of 20 meters, and then I'm going to create an array of that. And actually I'm going to create one extra block that will serve as our downstream boundary, because as I will show you, we need all the water that comes into needs to go somewhere, and I will just reserve this last block to basically absorb all of the water flowing out of the system. So I'm going to use the stream. Let me add one stream component here. So this is my stream component. I'm going to assign some properties to it. So now in GIFMod, we need to provide an area, a bottom area. Now, what I'm going to assume is, even though it doesn't matter, I'm going to assume that the depth of water in the plug flow reactor is 1 meter, and the width of the channel is also 1 meter. Okay, and the length is going to be, length of one single block is going to be 20 meters, and we're going to need 10 of them. So the bottom area is going to be 1 meter times 20, which is going to be 20 square meters. So that's what I'm going to enter. I'm going to enter 20 square meters for the bottom area. Then and then the initial water depth, as I said, is going to be 1 meter, and they're going to stay at 1 meter. Then I'm gonna enter a Manning roughness coefficient, because probably GIFMod is gonna give me an error if I don't have a Manning roughness coefficient for a stream, even though we are not gonna use this because we're gonna have a completely controlled flow. So we will not use the hydraulic feature of GIFMod to calculate the hydraulics for us, but we're gonna just fix the flow going through each of the blocks. And then okay, so a few other things that I'm going to provide that is going to be useful when I create an array. I'm going to enter the width. So the width is going to be 1 meter, and the length is going to be 20 meters. And I think that's pretty much all I need for my first stream block. Now what I'm going to do is that I want to create an array of these stream blocks. I'm going to create an array with 11 columns. 11 columns and I don't know, just one row. And the 11th block will be used as kind of a dummy block that will absorb all the outflow. So I'm just going to right click on the stream block that I just created, and I'm going to click on make array of blocks. And this is what we get. And on my Linux version, unfortunately, some of these labels are not clearly shown. I think if you work on a Windows version, they should be clear. So what I'm going to do is that I will choose this horizontal 2-dimensional array, and the number of columns. Now the second one is the number of columns, and I'm going to enter 11. And the rest of the things are populated automatically because we just provided the length of each of the stream blocks. So we can have horizontal distance between the cells in X direction is going to be 20 meters, which is correct. So now I'm going to click on OK, and what we'll get is our entire Plug-Flow Reactor. So okay, so a few other things. So I'm going to first do the hydraulics. As I said, what I'm going to do is that I'll just essentially configure the model so that the flow is equal, and hydraulically we are under steady state condition. That means the flow going into and out of each of the blocks is the same, and that basically the volume of each of the segments, the volume of water or storage in each of the segments is not going to change with time. So in order to do that, what I'm going to do is that I'll need to create this text file. So let me just go here, and I'm going to go to my documents, and I'm going to create a new folder, call it GIFMod PFR example. And under this, okay, actually I need to go to my text pad or text editor. You can use any text editor you want. So I'm going to open this, and this is how it works. So basically, technically I need two text files. One is going to be some sort of prescribed flow that I'm going to talk about later. And then this one that I'm creating right now is just the inflow, and actually the thing is that I will use this file as my prescribed flow too. That, I mean, in this particular case we can do it. So the first thing I'm going to type is I'm going to talk about the names of the data or time series data that I'm going to put here. So what I'm going to have is a flow. And then later on, I want to also do basically transport. So I need a time series for the concentration of, in this case, BOD in my inflow. So I'm gonna do it right here, even though I haven't introduced the BOD in my GIFMod model yet. So I'm gonna add the BOD. So we have two time series, and I need to have 4 columns here. 2 of them is going to be for times of flow and BOD, and the other 2 are going to be concentrations in the inflow. So I'm going to have basically all I need is 2 data points. So I'm going to start from time 0, and the flow, as I said, is going to be 100 cubic meters per day. And again, time 0, this is for BOD concentration, and we decided to assign a value of 4 milligrams per liter for BOD in the inflow. And the second basically data point is going to be just identical with the first one, except for it's going to be at a different time, and GIFMod is going to essentially interpolate the values in between. So all I need to do, I know that the duration of the simulation is not going to be more than 10 days. So I'm gonna say, you know, the second data point is at day 10, and then the values are pretty much the same, right? So that's what I create, and then let me just save it in this folder that I just created, and I'm gonna call it let's say inflow Plug-Flow Reactor .txt. So this is my inflow file. I can just minimize this and go back to GIFMod. So I'm going to now click on my first block, and I'm going to assign this inflow. So the inflow is going to the first block. So I'm going to just click on inflow time series right here. We have inflow time series. I'm going to click on the box in front of the you know, label box where it says inflow time series, and then I'm going to go and pick my inflow file that I just created. So I'm going to open that. Now to check and make sure that everything is fine, I can just right click on this first block, and I can look at flow, and as you can see, it's 100 from day 0 to day 10, and I can also look at the BOD, and it's 4. So everything looks fine. And now one thing I want to do, I want to make sure that the flow, that GIFMod is not going to use Manning's equation, for example, in this case, to calculate the flow. I want to basically impose a flow that is going to be uniform throughout. So in order to do that, the first thing I'm going to do is that I'll go to settings, I'll click on project settings, and then there's this option called let me expand this a little bit, steady state hydraulics. This doesn't actually mean steady state hydraulics, this means quasi steady state hydraulics. So what this option does is if I turn it on, or if I switch it to yes, what happens is that instead of solving the hydraulic equations, what GIFMod does is they will try to fix this, basically to set all the inflows and outflows into each of the blocks to be equal to each other, so that the storage of each of the blocks doesn't change, and then it will solve for the flow, right? Now one thing to point out, I have to somehow at this current state, the system is sort of underdetermined if I do it, because it's not clear for GIFMod whether it should you know, where it should impose some sort of a constraint on flow. Basically is I mean, we can't really have an inflow to the system and have the storage of all of the blocks to be you know, to remain unchanged with time, right? So what I'm going to do, I want to find a way to say, you know, relax one of these constraints. That's going to be our downstream, and basically preserve the constraint for all other blocks. Okay, so in order to do that, what I'm going to do is that I need to change the let me zoom in here. I'm going to change the flow, essentially the way the flow is calculated in this. It can be any of the links, but I'm going to do it on the first one. So I'm going to say you know, impose a flow essentially on this connector, right? So what in order to do that, I'm going to select this connector, and then I'm going to change the type from the default one to prescribed flow. Okay, so just click on prescribed flow, and if I do it, then it's going to ask me for a prescribed flow, and then I'm going to provide the same inflow file that I just created. Because you know, that's what I want. I want the flow into this you know, stream block to be equal to the flow going out, and it can just, you know, get the flow from the same file. So I'm going to click on prescribed flow option, and I'm going to select the same file. So if I now right click on this property and look at the flow, I'm going to get the 100, Now, at this time, I can actually check whether, what I've just came up with works fine. So let me just save it, and I'm going to save it in the same folder. Let's call this Plug-Flow Reactor example. Okay. And let's see how things will go. So just clicked on run. No errors so far. 100% complete, and there's nothing interesting to look at. I just want to make sure that the flow in all of these links is 100 cubic meters per day. Just look at the flow and you'll see the 100, so everything looks fine. Now the other thing is that if I look at the last block, which is my dummy block, its storage should go up linearly, and that's what's happening. So it starts from 20 and it keeps on going up linearly, and that's what I expect. For the rest of them, the storage has to be constant. So it is constant, and it's 20 cubic meters per I'm sorry, 20 cubic meters. So okay, next I want to do the water quality modeling. So the next step is that I'm going to introduce this constituent called BOD and then assign some properties to it. So I'm gonna click on water quality, and then I'm gonna right click on constituents, and I'm gonna add constituent. Now make sure that the name of this constituent has to be the same exact name as we put in our inflow file. So it's gonna be BOD. It should be all cap, just like what we had, and that's it. So I put the BOD. At this time, basically I haven't entered any reactions for BOD, so it's basically going to behave as a conservative tracer, right? So if I run, I now should get some results for the concentration of BOD in my blocks, right? So let me expand this a little bit, and then I'm going to zoom in. Yeah. So I'm going to run it now. So this is what we get. And now I can look at, let's say, the concentration of BOD. So for example, I'm going to pick this stream block number 6, and I'm going to look at the BOD concentration. And as you can see, it's going up. I expect it to eventually reach to 4, but it hasn't happened. So I better increase the duration of my simulation. So I go to project settings, and then I select this simulation end time, input a number, and I change the simulation end time to 5. Now let's do it again to make sure that the system reaches some sort of a steady state with this conservative tracer. Okay. So the simulation ends, and then now I just look at my, the block number 10, which is my last, actual block, and you see that we get pretty close to 4. Now, in theory, this has to be just a step function, because we have a step release. But then the fact that it's, you see this curved behavior, that's due to numerical dispersion that is happening. If I want to reduce that numerical dispersion, I need to refine my model furthermore, which I'm not planning to do it. So that's it. And then next and last step, I'm just gonna add a reaction at basically let's say mineralization of BOD, for example, decay of BOD. So what I'm going to do is that I'll first add this reaction parameter. So I'm going to add a reaction parameter. I'm going to call it, I don't know, let's call it KD. And the value, as we said, it's going to be 0.1 per day. And then I'm going to add the build my reaction network. So I'm going to right click on reaction network, and I'm going to click on open reaction network window, and this is what we get. And so I'm going to have one process that is going to be decay, The process rate is going to be KD times BOD, okay, which means a first order decay. And you can easily, you know, come up with other, you know, reaction rate expressions if you want to do monode, if you want to do second order or anything. And then the stoichiometric constant on BOD is going to be -1. Okay, so that's pretty simple reaction network. And let me save my model, and now I'm going to run it. Okay, so we got some results. Let's look at the concentration. So concentration of BOD in the second, the second block. As you can see, it doesn't go up all the way to 4. It basically reaches a steady state at a number that is lower than 4. I can look at maybe BOD at other stream blocks too. Let's do some comparisons. I'm going to copy this and paste it here, and that's what you get, right? So the other thing I can do is that I can look at the spatial distribution of concentration. So if I click on post-processing, water quality, and then pick BOD, this is what I'm getting. So initially at time 0, the concentration of BOD is 0 everywhere. And as I, increase the time, it'll start, going up. And at the end, we get to this steady state kind of distribution. And now the last one is, it's basically essentially we have this effect of dilution. So you should really look into the concentration in this last dummy block if you want to see what's going to be the effluent concentration of our Plug-Flow reactor. And that's pretty much it. So please look for the future videos. What I'm going to do is that I will just use this model, and I will add some maybe more complex reactions involving multiple components. For example, we can do sort of like something like a Streeter-Phelps modeling when we have BOD and oxygen, and maybe we can add nitrification, denitrification, and things of that nature too. Thank you for watching, and look for the future videos.